Okay, and finally, we take a look at our third form of energy that we're going to quantify, and this form of energy is called elastic potential energy. Again, we start by looking back at this particular slide. We've already talked about, you should have seen a video or saw a lecture in class about kinetic energy, and we've recently looked at gravitational potential energy. We're going to skip over some of these other forms, a little bit harder to quantify, and we're going to move right down here to elastic potential energy. Now, the second portion of this unit will get into electricity, so we'll look at this one later on. But for right now, let's focus in on elastic potential energy. It's the energy due to stretching or compressing objects. Let's go ahead now and take a look at this slide here. So elastic objects, things like springs, rubber bands, etc., tend to return to their original shape when we stretch them or compress them. Hence, we can store energy in that shape, and then of course later we can return it. Some obvious examples: a bed spring here, if you put your hand down on that thing, it's going to be able to just sort of spring back up on its own, just because we're storing some of the work that we do in the shape of that spring. Tennis balls and tennis strings themselves are elastic, which allows us to be able to hit that ball with much greater speeds than if they were inelastic. Golf balls, same idea. Pole vaulting, that elastic pole is able to bend and store some of the kinetic energy of that object's motion there, store it into the elastic potential energy that can then be transformed into GPE as they go over that bar. And if you've ever shot a bow and arrow, you know that you pull back that string. The energy is not actually stored in the string there. It's actually stored in the bending of that bow. And when we release that, of course, the bow bends back to its original shape, and in the process does some work on the arrow to be able to speed it up. Now, as before, the stored energy is ideally equal to the work done in changing the shape of that object. Now, we don't ever get 100% of the energy out from what we put in, so we never get all of that energy out, but nonetheless we can still get a fair amount. PE belongs to a system of objects. So what are the two objects involved in EPE systems? You see, we have you might look at this and say, well, there's a hand and a spring, and there's a ball and a tennis racket, and there's a golf club and a golf ball, and so forth, but that's not really what's going on. Remember, the spring itself is elastic. It doesn't need to have the hand there in order for it to contain elastic potential energy. It's really from molecule to molecule, and if you think about how solids are constructed, there's one molecule attached to another molecule, and those are through electric bonds, and when we compress or stretch that, it has a tendency to return to its original shape. Now, I want to show a short little simulation here on that, and see if we can understand how that works. So take a moment and pull this simulation up, and we see something that looks like so. Let's see. I can go ahead and just leave that like so. I could consider this to be a spring that I move up or down and start this, and you can see that when I sort of start this into motion, we can sort of have one object sort of cause other objects to move. I'm sort of like doing some work here, and when I pull that thing down, do some work on it, I can store some energy in that shape, and when I let it go, of course, it's going to sort of convert some of that energy back into other forms, and so you can see there's energy of motion here. Now, if you've ever been on a trampoline, let's put this into 2D, and let's add a bunch of these things on here for a minute. If you've ever been on a trampoline, you know that when you jump on that trampoline and you sort of displace a portion of that, the other portions of the trampoline sort of work to spring you back up. Let's just see how that works. If I bring this thing this way, you can see that just moving one of those molecules is able to interact with all the other ones through these electric forces. Now, we're using springs to model that electric force, but elastic potential energy really is energy due to the electric force that sort of holds molecules in their shapes. So if I take this thing and start whirling this thing around here, you can see evidence of elastic potential energy being converted into other forms as that moves. And I always found that to be sort of interesting to watch. Okay, so maybe you enjoy that as well. Go to that PhET simulator and play around if you'd like. Now, based on that, we can go ahead and start to define or start to quantify elastic potential energy using this definition here. The energy stored is ideally equal to the work needed to change the shape. Now, this is sort of hard to do in a video. So oftentimes in class, if you were in class when we do this lecture, we would take a rubber band and we'd sort of stretch it to determine how much work we do in stretching that rubber band. and then we would try to calculate that using this technique. So if you're only watching this on a video, it's not nearly as easy to understand. This equation, work is equal to force times distance, is true, but that's only if the force is constant. If the force is variable, we have to look at it in other ways. If you've ever pulled back a bow or stretched a rubber band, you know that it gets harder to stretch the further you stretch it. So the force is definitely changing. Now what I want to do is in class we would hook this rubber band up to a pole and just sort of pull it with a Newton scale and then measure force as a function of distance. Now I typically do that with Nemo being shot around the room, and so I'm going to go ahead and change these things so that the numbers that I give you are very similar to the ones that we did in class. I stretched this thing about 60 centimeters, and so I'm going to go ahead and add those here as various lengths, 10 centimeter increments. And so if I stretch that thing from its relaxed length all the way out to a full length that's stretched 60 centimeters, and then measure the amount of force necessary to do so, we get something that looks like this. It's about 1.5 newtons to stretch it about 10 centimeters. Then to stretch it another 10 centimeters, it only took about 2.2 newtons to get it there. And then to stretch it another 10 centimeters, so 30 centimeters total, is about 2.7 newtons. Another 10 centimeters is about 3.2. And to get it one more group of 10, we got that to about 3.7. And the last one was about 4.1. Okay, so we see a gradually increasing force as I stretch it. I could calculate the work by using the average force. So just add those things up and divide by 1, 2, 3, 4, 5, 6. We could do that, but there's another way to do that. And that's to graph the force versus the displacement and then take something called the area underneath the curve. And that's what I want to do on this particular video. So if I were to take the distances and graph those down here, and the force and graph that here, let's just go ahead and do that quickly. Zeros and zeros, and let's make that 10, 20, 30, 40, 50, and 60, and then 1, 2, 3, 4, and just quickly plot those. We got 10 goes to about 1.5, 20 about 2.2, 30 2.7, 40 about 3.2, 50 3.7, and 60 about 4.1. Again, we're just trying to get somewhat of a rough sketch here. I'm going to try to draw that as accurately as I can once I've got those dots connected. I can actually find the work done by considering the area underneath that curve. And to help you understand what I'm doing here is I have an increasing amount of force as I stretch it through some of these distances here. Well, what force do I use? Do I use the one at the beginning? Do I use the one at the end? In reality, what we're going to do is we're going to just try to find the area underneath this curve by counting up these blocks. Let's go ahead and take this particular block there. Let's just draw it a little bit bigger over here. Make it easier to understand what we're doing. This is a 10 centimeter length there. Right? This is 10 centimeters. I'm going to put that in as 0.1 meters. And this height was 1 Newton. So when I look at this here, I see that that would represent a constant force, 1 Newton of force, acting over a distance of 1 meter. And so this would be 0.1 joule of energy. Right? So that particular block is 0.1 joules of energy. Now all I need to do is just count up all these blocks to see how much total energy I have. Now because I can't count this as a whole block, what I'm going to do is I'm going to count anything more than 50% as a whole, and anything less than 50% not at all. So I'm going to count this one. I'm going to count that. That's 2, 3, 4, 5, and 6. Go up here to 7. This is 8. That's 9. That's 10. I would count this one as more than half. This one is pretty close. I'd say because these two are almost the same, I'm going to count only one of these and not the other. So let's go ahead and count this one, 12. And not count this one. Okay, so that way any overestimation that we have here is sort of taken up there. So now I've got 16 of these blocks underneath that graph. Since each one of those blocks represents 0.1 joules, I can go ahead and determine that total work to stretch that band to be 16 blocks with each one being 0.1 joules. And for that I get 1.6 joules. If you want, you could go through and find the average there, and you should see that when you calculate it, it's going to be pretty close to 1.6 joules. By most efforts, this is the more accurate way to do that than trying to take an average value, but nonetheless, it should be close. Okay, and so that's the only way that we have right now to calculate the elastic potential energy is through this graphing technique, and there are other ways to do it with some other equations, but I think this should suffice to show how the energy stored by changing the shape of an object can come back out as other forms when the object returns to its original shape. And we can certainly find that amount of energy, that amount of work we do in stretching it by this technique. And that completes this video.